You know that phone in your hand? Or the car keys on your desk? Have you ever really stopped to think about how they go from just an idea to a physical thing you can actually hold? Well, today, we're going to pull back the curtain on that whole process. We're going on a journey to explore the hidden principles that turn concepts into the objects that shape our world.
So let's kick things off with a super simple question. Have you ever tried to pour tea before you've boiled the water? Of course not, right? It's just wrong. You'd end up with a cold, wet mess. Well, that incredibly simple, intuitive rule that some things just have to happen in a specific order is the absolute bedrock of all complex engineering.
In engineering, we call this the order problem. Some steps are sequential. They have to happen one after the other. But then you've got this other thing, the concurrency problem. Now imagine two people trying to pour boiling water into the same tiny cup at the exact same time. Again, total chaos. So you see, the real challenge in designing anything great isn't just about what you build, it's about how you orchestrate the whole process. It's all about mastering what happens first and what can happen at the same time.
So, here's our game plan for today. We're going to start with that core idea, the order of things. Then, we'll see how you create a digital blueprint. After that, we'll look at how we have to design things for the real world, for the factory floor. And finally, we'll dive into two amazing ways we actually bring those designs to life, by literally printing them out of thin air and by carving them out of a solid block.
All right, first things first, let's really nail down this foundational idea, the order of things, by looking at sequential versus parallel processes. A sequential process is just like our tea example, right? Each step has to finish completely before the next one can even think about starting. And its real power? It's predictable. If something goes wrong, it's way easier to figure out where the problem is. The opposite of this would be a parallel process, where a bunch of things are happening at once. Sure, it's faster, but it is way, way more complicated to manage. Okay, so we get the importance of order. But how does a spark, an idea that's just floating around in your head, become a super detailed plan that a machine can actually understand and build? Well, the answer is the digital blueprint. This right here shows the modern journey of a product, and it's all powered by something called computer-aided design, or CAD. Notice how it's a really carefully ordered sequence. You start with the big idea, then you design the electronic brains, lay out the whole circuit board, and then build a virtual case around it. And here's the really cool part. We can even simulate real-world physics, like will it overheat, will it break if you drop it, all before a single physical part even exists.
And this is where two totally different worlds have to collide and play nice. On one side, you've got ECAD, or electrical CAD. That's for all the complicated circuits. On the other side, you have MCAD, or mechanical CAD, for the physical structure, the case. The absolute magic of modern product design is getting these two to work together perfectly. I mean, what good are the electronics if they don't fit inside their shell, right?
And boom! This shows you exactly what I'm talking about. This is the Radiant device, and you can see perfectly how that purple circuit board, the PCB, is designed to fit just so right inside its custom-made enclosure. That is ECCAD and MCCAD integration in action. It's beautiful, isn't it? So we have a perfect digital model. Everything fits together like a dream. But a beautiful design that's impossible or just crazy expensive to actually build? That's not a product, that's a fantasy. This is where we have to build a bridge from that perfect digital world to the messy physical reality of the factory floor. This brings us to a really important idea called Design for X, or DFX. And as you can see from this wheel, that X can be anything. It could be manufacturing, assembly, cost, even reliability. It's a huge mindset shift. It means you have to be thinking about every single stage of a product's life while you are still designing it. Because a brilliant concept that can't be built affordably is really just an expensive drawing.
Now, the two most famous of these are DFM and DFA. The easiest way to think about it is like cooking. Design for manufacturing, or DFM, is all about making sure each individual ingredient, each part, is easy and cheap to make. Design for assembly, or DFA, is about making the final recipe, putting all those parts together as simple and foolproof as possible. They're really two sides of the same coin. So what actually makes something easy to assemble? Well, think about the best piece of flat pack furniture you've ever put together. The best ones have parts that just drop in from the top, they line themselves up without you having to wiggle them around, and maybe they even click into place without any tools.
Every single tiny design choice that follows these rules saves time and money on the assembly line, and it drastically cuts down on the chance for mistakes.
Think of it just like this perfect puzzle piece. The best design for assembly makes the whole process feel, well, obvious. Each part has a very clear home, it only fits in one way, and it goes in smoothly. You're basically designing a puzzle that solves itself.
Okay, so we've got a smart blueprint that's designed for the real world. Now for the fun part. How do we actually make the thing? We're going to start with a pretty revolutionary process that builds objects up from nothing. This is additive manufacturing.
We'll kick it off with the OG, the original, stereolithography, or SLA. This was first patented way back in 1986. The main idea here is to build an object, one tiny, paper-thin layer at a time, by using a UV laser to cure, or harden, a special liquid plastic.
So let's break down how this actually works. If you look at the schematic, you can see a UV laser, that's number 4, and it's being aimed by a mirror, number 5. It basically draws a slice of your design onto a super thin layer of that liquid resin, which is number 2. Where the laser hits, the resin hardens instantly. Then the build platform, number 3, moves down just a tiny bit, and the whole process repeats for the next layer.
So why would you pick SLA? The biggest reason, hands down, is precision. It can produce parts with absolutely incredible accuracy and a super smooth surface finish. This makes it perfect for things that need a lot of detail, like prototypes, custom jewelry, or even things like dental implants.
Now let's talk about a method you might have actually seen in person, fused deposition modeling, or FDM. Honestly, the easiest way to think about it is as a very precise, robot-controlled hot glue gun that builds an object one line at a time.
As you can see here, you have a big spool of solid plastic filament. That gets fed into a heated nozzle, the extrusion head. The head melts the plastic and draws out the first layer of the object. Then the platform drops just a little bit, and it repeats the process, with each new layer literally fusing to the one below it.
Now, FDM is super popular because it's pretty fast and it uses materials that are affordable and durable. So what's the catch? Well, it's all about strength. Because the object is built in layers, it's kind of like a block of wood. It's strong along the grain, but it's much weaker between the layers. There's a fancy word for this, anisotropy, and it just means the final strength of the part depends more on how well those layers stick together than on the plastic itself.
Okay, for our final stop, we're going to look at a completely different way of thinking. Every method we've looked at so far is additive. They build something by adding material. Now, let's flip that on its head and look at a subtractive method, where we start with a solid block and take material away. This is CNC machining. It stands for Computer Numerical Control, and it's basically the exact opposite of 3D printing. Instead of adding material, you start with a solid block of metal or plastic, and you use a super fast computer-guided cutting tool to carve away everything that isn't your part. It's like a digital sculptor, just revealing a precise, incredibly strong component from inside that raw material.
So there you have it. We've gone all the way from a simple rule about making tea, to creating a digital blueprint, to designing for a factory, and finally to creating real objects by printing them layer by layer or carving them from a solid block. This journey from a simple idea to a physical object is one of the most fundamental things we do as people, and it all starts with understanding the process. So the only real question left is, what will you create?